Hello, today is the start of the 6th week of this course, and till so far what we have done is we have developed differential equations which govern the mechanics of laminated composite plates. So, starting this week and for next couple of weeks, we will use these equations to solve some practical problems. So, that way you will have an understanding, you will develop some understanding as to how to use these equations for real life problems. Today we will start with the case of a semi-infinite plate. Now, this is an idealized case of a plate which is extremely long in one direction and not that long in the other direction. So, this is the geometry of the plate. So, we are going to discuss semi-infinite plates. Now, theoretically its length should be infinite, but we will that is an extreme case, but a plate which is very long in one direction and not that long in the other direction, we will call it a something close to a semi-infinite plate. Now, this plate we could have some external load on it, and we will assume that the external normal load on the plate is q newtons per meter. So, that is the load intensity. So, this is a uniformly distributed load. If I look at this plate from the other end, it will look like this. So, this distance, this dimension is width, the width of the plate is b, the length of the plate is a, and the height of the plate, let us say it is h. So, when we say that this plate is semi-infinite in its length, it implies that a is extremely long compared to b. A is extremely long compared to b. And let us set our axis system. So, this is the midpoint of the plate. So, my x axis is here and that is my z axis, and y axis goes normal to the direction of the board. Now, if that is the case, consider that there is a plate which is very long, and if I bend it, it will only develop curvature in the x direction. The curvature in the y direction, it will not be that much significant. So, because of that, we can say that because the plate is very long, we can say, because of the geometry, we can say that all the differentials in the y direction are approximately equal to 0. And because of this, so if all the differential in the y direction, partial derivatives in y direction are approximately 0, what that means is that the derivative in the x direction, we can approximate it as the total derivative, because there is no derivative in the y direction. So, this is the implication of a semi-infinite plate. Now, we want to see that when we subject this plate to an external load of q, how does this plate bend or deform? And as we discussed earlier, we also need to know the boundary conditions for such a problem. So, we will have 4 different problems which we will try to solve. So, what are these 4 problems? So, I will just draw a schematic. So, first there is case A. In case A, let us say this is the plate and it is simply supported on both sides, but the nature of simple supports is different. So, it is the simple support is not allowed to roll on a base at one end, but on the other end it can move. So, if that is the case, then what is the boundary condition here? Because it is simply supported, u is 0, again it is pinned. So, v is 0, w is 0, and because it is simply supported, moment is 0 at this end, and because my axis is from here. So, this is the negative edge of the plate. So, I will say u minus, v minus, w minus and mx minus, these parameters are 0. Now, on the other end, what is the condition? So, because this simple support is free to roll, it is free to roll, and anything can be free to roll only if it is not exerted subjected to any external force. So, instead of u being 0 or at this end, we will say that nx plus is 0, because it is free to roll, there is no external force acting on it. Similarly, instead of v being equal to 0 at this end, we will say that nxy plus is 0, that is the force in the y direction, force per unit length in the y direction is 0. The third thing is that it is simply supported. So, there is restriction of w, so w is 0, and the fourth is mx plus is 0. The other thing is, what is the lamination sequence? The lamination sequence is 0, 90, symmetric. So, this is the definition of case A. Next, let us look at case B. We will do 4 cases. Okay. So, in case B, it is similar geometry, but the plate is pinned and fixed on both the ends. So, what are the boundary cases, boundary conditions? U minus equals 0, v minus equals 0, w minus equals 0 and mx minus equals 0. And on the positive side, u plus equals 0, v plus equals 0, w plus equals 0 and mx plus equals 0. And the lamination sequence is still the same, 0, 90, symmetric. So, it has 4 layers, 0, 90, 90 and 0. So, that is our case B. Then we will do 2 more cases. Case C, again same type of plate, and the boundary conditions in this case are similar to that in case A. Okay. So, u minus, v minus, w minus, mx minus, all these are 0. And what is the boundary condition on the other side? Nx plus, nxy plus, w plus and mx plus, they are 0. So, you see that case C and case A, they have same boundary conditions, but the difference is that here the lamination sequence, we will say that it is not symmetric, and let us see what happens when the lamination sequence is not symmetric. Okay. So, that is case C, and then finally, we have the fourth case, case D, and the boundary conditions for case D are similar to case B. So, u minus, v minus, w minus, mx minus, all these are 0. And the only difference between D and B is that the lamination sequence for D is not symmetric. So, both all the cases have 4 layers, but in 2 cases we have symmetric lamination sequence, and in the other 2 layer cases, case C and case D, the lamination sequence is not symmetric. So, what is the question? The question is, for each of these cases, find U, V, W. We should find what is the value of U, V and W. Okay. And then if we know U, V and W, then we can also find Nx, Ny, Nxy, Mx, My, Mxy. So, we have to find for all these cases all these parameters. So, that is the problem. So, actually before we start with case A, we will first, what we will do is we will solve the problem to a point till no boundary conditions are applied. First we will start solving this problem till we reach a stage that no boundary conditions is applied. So, till that point the solution will be common, and then the moment we start applying boundary conditions and the values of A, B, D, then that solution starts diverging. Okay. So, first we will develop a common solution, and then we will apply the conditions for A matrix, B matrix, D matrix, and also boundary conditions, and in that way we will develop 4 different solutions. So, we know that del over del y equals 0 and del over del x equals d over dx. Okay. So, if that is the case, then our governing equations governing differential equations, let us see how they change or get simplified. So, our first governing differential equation was del nx over del x plus del nxy over del y equals 0, and this simplifies to d over dx nx equals 0, right, and if I integrate this I get nx is equal to C1. So, till so far we have not applied any boundary condition and we have not applied any stuff related to lamination sequence. So, this is valid for all the cases. What is the second governing equation? Del nx y over del x plus del ny over del y equals 0, and once again del over del y is very small and del over del x is same as d over dx. So, what we get is d nxy over dx is equal to 0, and that gives us nxy is equal to C2. Again this equation, this value, so what it means is that in all the 4 cases, nx will be constant throughout the length and y also will be constant throughout the length of the plate. And then what is the third equation? Second derivative of mx plus 2 del 2 mxy over del x del y plus del 2 my over del y square plus q. So, it is a function of x. Now, we know that anything which is partial derivative of y is 0. So, this is gone and this is gone, and this thing it becomes a total derivative, and also we know that Qx in our case is constant. So, it is Q. In our case we are applying the load uniformly on the entire plate. So, what I get is, so this gives me second derivative of mx is equal to minus q, which is a constant, and this gives me mx is equal to minus qx square. Actually, I will write it below so that it is cleaner. So, it gives me mx, if I integrate it twice, I get mx is equal to minus qx square by 2 plus C3x plus C4. So, that is the third equation. So, these three equations 1, 2 and 3, these are common to all the 4 different cases. So, these are common to all the 4 different cases. So, now what we will do is, we will now solve case A. Okay. We will solve for case A. So, what is case A? Case A is this thing. And of course, there is constant uniformly distributed load here, and its intensity is Q newtons per meter, Q newtons per meter. So, the boundary condition here is U minus equals V minus equals W minus equals Mx minus equals 0, and in the other case it is Nx plus is equal to Nxy plus is equal to W plus equals. So, these are all mid plane displacements is equal to Mx plus equals 0, and the lamination sequence is 0 to 92 symmetric. That is the lamination sequence. So, what we will do is, because we have cross ply laminate.
So, if I can memorize, there was 0 and 90 symmetry. There was 0, 90 symmetry.
Yes. So, this is not 0 2, it is 0 and 90 symmetric. Yeah. So, because we have a cross ply laminate, and what does a cross ply laminate means? That all the layers are either 0 degrees or 90 degrees. Just because of that, we can say, we have learned this earlier, that A16 is equal to A26 is equal to D16 is equal to D26, this is 0. And also the laminate is not only cross ply, it is also symmetric, because we have symmetric laminate. We can say that the entire B matrix is 0. Okay. We know that N and M, if we have to relate with strains, then this is equal to A, B and D times mid-plane strains and mid-plane curvatures. Okay. Now, it just turns out that this B matrix is 0. So, what we get is that Nx is equal to A11 epsilon x naught plus A12 epsilon y naught plus A66 gamma xy naught. I am sorry, not A66, A16. A16 gamma xy naught. But we know that A16 is 0 because it is a cross ply laminate, and also we know for this thing. So, what is epsilon y? Epsilon y naught is del v naught over del y, and because it is a partial derivative of y, this is also 0. Okay. Similarly, gamma xy naught is del v over del x naught plus del v naught plus del u naught over del y, and so this is again, if I just ensure that partial derivative with respect to y is 0, then that means it is equal to dv naught over dx. Okay. So, anyway, so this is there. So, in this relation for nx, A16 is 0 and also epsilon y is 0. So, nx becomes A11 epsilon x naught, and what is epsilon x naught? It is equal to A11 times du naught over dx. It should have been partial derivative, but because it is d over dx. So, partial derivative because of this semi infinite plate is a total derivative. So, it just simplifies to this thing. Okay. So, we can write this nx is equal to A11 du naught over dx, and we have seen that from equation 1 this is a constant, nx is equal to C1 from equation 1. Okay. So, we can say that this is equal to C1. So, this gives me, so if I integrate it, I get u naught x is equal to C1 x plus C2 into 1 over A11. So, this is the fourth equation. So, let us call this, yeah, we will call this equation A. So, we have calculated, now we do not know what these values of C1 and C2 are, we will find that later, but what we are seeing is that u in this case is linearly varying over the length of the plate. So, what we will do in the next class is we will continue this discussion and we will solve for the entire problem for this particular plate in the next class. So, that concludes our discussion for today, and I look forward to seeing you tomorrow. Thank you.